the next presenter is me, so I get the privilege of introducing myself. And I'm going to share this screen over here. So you're seeing what I want you to see?
Yep.
Great. All right, I'm going to dive in. So my name is Alex Leith. I work at Geoscience Australia, currently work on the Digital Earth Africa project. Digital Earth Africa's vision is around providing routine, reliable and operational service using Earth observations to deliver decision-ready products, enabling policymakers, scientists, the private sector and civil society to address social, environmental and economic changes on the continent and develop an ecosystem for innovation across sectors. It's pretty hand-wavy, nice and fluffy kind of introduction. What I like to think of is that we are making Earth observation data more easily accessible over all of Africa. Not just continental, but the islands too. And I think that the way that this project is run, so I work on Digital Earth Australia, I used to as well. And Digital Earth Australia was founded on getting the Landsat data, unlocking the Landsat data. And the first project was literally called Unlocking the Landsat Archive. And back in the past, analysis-ready data wasn't really an agreed-on thing. And so getting that data that was captured from the satellite, turning it into something that is analysis ready, making that accessible was a really big deal. And the way that we did that is through lots of net CDFs on a file system. We're at a completely different paradigm now in that having all the data accessible all at once through essentially HTTP API is where it's at. So we used to have a supercomputer which you had to get permission to join on and be able to read the file system and think about all of that while you did it. Now you can just access all of the TIFFs anytime from anywhere in the world when you look at the USGS Landsat repository. Software was really hard to install, complex, bespoke, written from scratch in the case of the Australian Geoscience Data Cube. These days, there's standardized data science tools. People talk about Pangeo. Everybody's kind of used it. A lot of people know what a notebook is and launch it and use the same tools. When we're doing remote sensing using Python, practically everybody's using Xarray. When it comes to science, local, difficult to reproduce science, data on your laptop, bespoke little tiny net CDFs of your case study area. These days, we're doing collaborative data science, teams of scientists working the same way using Git, code reviews, a whole bunch of software paradigms, but scientists are doing it. And it's a fantastic way to be sharing, standing on each other's shoulders and collaborating. So in terms of cloud native, we don't produce analysis-ready data. We store it. Digital Earth Africa does. So we have a couple of buckets in S3 in Cape Town in South Africa, where we store and manage and maintain over 3 petabytes of data. One of our biggest products is Landsat data that we get from the USGS. And the way that we get that is these cloud native things. So they send an AWS SNS notification. SNS stands for Simple Notification Services. It really is just like a ping that you can subscribe to. It has a little bit of JSON in it. And that says there's a new scene that the USGS has produced. We grab that scene, stick that notification on a queue. We shift all of the cogs to South Africa. We update the STAC metadata that they produce to point to our bucket, and then we create our own notification, which says to us, there's a scene in our bucket. And that's public, so people out in the community can subscribe to that notification and do whatever they want. But we subscribe to it, so we dog food these notifications and we index it into the Open Data Cube and create some scene-based derivative products on it, basically as soon as we can in real time. What that means is that on February 10th this year, USGS released Landsat 9 data. The next day, it was available in Digital Earth Africa in Cape Town with the data down there. I basically had to edit a bit of configuration that said include this sensor as well as Landsat 5, 7, and 8, and we have the data. It's there. So another aspect of big data is being able to access all that data. So talking about kind of, so I want to talk about this analysis here. So this is the geometric median. The input to this is 65,000 Landsat 8 and Landsat 9 scenes that cover 2021 over all of Africa, as you can see on the right there. We want to produce a cloud-free summary of those. So for a given region of interest, find all of the scenes, mask out all the clouds, work out the middle observation, the median pixel. It's a synthetic observation. Write that out, throw away the rest. So you basically touch every single pixel. We're able to do this over the entire year, 65,000 scenes on 70 spot instances in less than an hour, and compute cost is less than $100 US. Being able to move this fast, so we were able to do that within 2 weeks of the Landsat 9 data being available. Being able to move this fast is simply not possible on without using the cloud. This is what it looks like. This is the kind of resource consumption that uses 14 terabytes of RAM. Again, it only cost us $100 because we only used it for an hour. And we get this beautiful image on the right at 30-meter resolution over wherever there is Landsat. And up close, it looks really pretty. What I'm really proud of is that it's not just the kind of data science cloud engineer people that can do this kind of analysis. We're able to get our science folks doing it too. So we've got a continental crop mask at 10-meter resolution, which for every pixel says yes, no, and the probability between 0 and 1 of whether that pixel is cropping land. It took a year to develop the method and run the first region. There's 8 regions in total. The last region took a week to basically produce, and we're able to rerun the entire thing, it's continental 10 meters, in about a week. Another really cool, so this is crop mask on the right. Another really cool product. Yeah.
You're running a little long.
I'm going too long. All right, I'm going to skip over this. Our science guys can do some really cool stuff, and it's pretty. So check out, ask me later, and I'll talk about it more. How about I stop there? You can read the conclusions, ask me questions. Thank you very much for your time, and I'm sorry I went too long. Ryan's asking about Argo workflows, and I do want to say that I love Argo. Argo is a fantastic workflow tool. The way that we use it now is for a big data processing job. We put tasks on a queue, and then we run X containers that have been templated by Argo, and they sort of take the jobs off the queue and do them. But I've got a whole bunch of different example scripts that we run with Argo, so Python scripts in a Docker container, and a range of example Argo workflows, some that we run like routinely every 7 minutes or an hour, and some where we do it once as a get data from here, change it, write it out there. Argo's great. It's a fantastic way of stepping back from the detail of Kubernetes a little bit and making it really easy to use. Matt has asked what the difference between a geomedian and just calculating a per band median value is. And I don't actually know the answer to that, but I actually can't explain it very well. Sorry, Matt. I have to defer to someone with more knowledge than me. Plus, I've had the microphone for too long. So